For centuries, the Shroud of Turin has defied every scientific explanation. Until now. Researchers unleashed a supercomputer to scan its surface, and artificial intelligence detected a symmetrical signal and a mathematical code embedded in fibers thinner than a virus. That discovery revealed a hidden three-dimensional map, physically impossible to create by hand, and it raises the prospect of an event unknown to physics. But if this is not an artwork or a fake, how did such a precise pattern survive undetected for 2,000 years? The answers challenge everything we thought we knew. The first clue begins with what the artificial intelligence uncovered. A full-length digital scan of the Shroud's linen was fed into a neural network designed for anomaly detection. The system, built on classical computing with convolutional layers and principal component analysis, processed ultraviolet fluorescence images captured by the STURP team in 1978. As raw data streamed through, the network flagged a recurring intensity pattern across the fabric, one that could not be explained by random stains, weave irregularities, or known environmental damage. The AI heat map did not just highlight the well-known facial and body features, it revealed a symmetrical signal running the length of the cloth, repeating at intervals that matched neither the herringbone weave nor historical burn marks. Principal component analysis stripped away surface noise, isolating eigenvectors that mapped subtle molecular differences between image and non-image zones. The anomaly score, an internal metric for statistical outliers, spiked in regions corresponding to the faint body image, but remained silent in the background linen. This suggested the presence of an underlying structure not visible to the naked eye, and not accounted for by previous photographic or chemical analysis. Frequency plots generated by the AI showed periodicity in the brightness values, hinting at a mathematical relationship rather than random deposition. The network's outputs, heat maps, eigenvector overlays, and anomaly graphs formed a dossier of computational evidence. Each graphic pointed to a non-random symmetrical pattern embedded at a scale finer than any known artistic or mechanical technique from the medieval era. The lead computational scientist, tasked with interpreting these results, noted that the dataset behaved less like an artwork and more like a coded record, a signal waiting to be decoded. The question was no longer whether the image could be explained by simple forgery, but what physical process could have produced such a precise and persistent pattern in the first place. Scanning electron microscopes zoom in on a single linen fiber, revealing a boundary between untouched background and the faint image zone. The difference registers at the nanoscale. The image resides only on the outermost 200 nanometers of each strand, about 1/400th the width of a human hair. No pigment or dye seeps below this delicate surface. Cross-sections show no evidence of brushstrokes, directionality, or mechanical pressure. Instead, subtle chemical changes, dehydration and oxidation, alter the cellulose, leaving the core of every fiber untouched. Transmission electron microscopy picks up clusters of nanoparticles embedded in the image layer, but not in the background. These particles, including creatinine-bound iron, are consistent with biological fluids from severe trauma, not with medieval paints or stains. Energy dispersive X-ray analysis confirms the absence of artists' materials: no vermilion, no ochre, no trace elements from ancient dyes. The image is a surface-level chemical alteration, not an applied pigment. Principal component analysis, or PCA, run on the ultraviolet fluorescence data, strips away the noise of weave patterns, scorch marks, and centuries of grime. What remains is a mathematical map. The brightness at each point on the image follows a precise relationship to the distance between the cloth and a hypothetical body. This is not shading or artistic modeling. The data fits a physical law. Intensity falls off with the cube of the cloth to body gap. When the PCA output is rendered in 3 dimensions, the result is a relief map of a human form, encoded not by hand, but by the physics of proximity. No known artistic technique can produce an image confined to the top 200 nanometers, with brightness mathematically tied to spatial distance. The evidence from microscopy and PCA confirms the image is a physical phenomenon, not a medieval forgery. The signal flagged by AI is anchored in the very chemistry of the linen, etched by a process that remains unexplained. In 1976, American physicists John Jackson and Eric Jumper brought the Shroud of Turin into a laboratory filled with NASA technology. Their tool was the VP-8 image analyzer, a device originally built to convert brightness data from lunar photographs into three-dimensional relief maps for the Apollo missions. When ordinary photographs were placed in the VP-8, the results were chaotic. Faces warped, features collapsed, and no depth could be extracted from the flat shaded images. But when the Shroud's image was fed into the machine, the VP-8 produced something no one expected. A coherent, lifelike three-dimensional relief of a human form, with accurate facial contours, body shape, and even the swelling of the cheek and nose. The VP-8 output depended on a simple principle. The brightness of each pixel was translated into height, as if the image encoded spatial information. For every normal photograph, this method failed because artists use shading and perspective, not mathematical relationships between light and distance. Yet the Shroud's image responded as if it had been formed by a physical process mapping the cloth's distance from an object beneath it. The result was so precise that it revealed anatomical details, eye sockets, lips, beard, and even the curvature of the hands, without any distortion. The relief was not an artistic illusion, it was a data-driven topography. Jackson and Jumper documented their findings in archival reports and presented them to the scientific community. Their tests showed that the Shroud encoded three-dimensional information in a way no other known image did. The VP-8 analysis became the first independent technological confirmation that the image carried embedded spatial data, decades before AI or digital enhancement. This result forced researchers to consider that the Shroud's formation involved a mechanism beyond paint, heat, or pressure, one that could register depth directly into the fabric's surface chemistry. When neural networks deconstruct the Shroud's image, the data reveals a phenomenon that defies ordinary explanation. The three-dimensional mapping, stripped of the cloth's weave and centuries of fire damage, points to a formation process that acted vertically, like a controlled burst of energy projecting upward from a body, not smearing or diffusing along the linen. The background linen remains untouched, its fibers chemically silent, while the image zone displays a razor-sharp boundary at the nanoscale. This clean separation suggests that whatever created the image was precisely limited to the space occupied by the body, ignoring the rest of the cloth as if following a confined, collimated path. Overlay analysts working with AI-enhanced archival scans noticed subtle circular distortions positioned over each eye. These features, almost invisible in the raw photographs, become clearer under digital enhancement. Their diameter and placement correspond with Roman lepton coins, minted under Pontius Pilate from 29 AD to 36 AD, coins known for their crude, uneven designs and unique markings. The match is not perfect, and the evidence remains controversial, but the statistical alignment between the coin outlines and the lepton's distinctive letters and symbols is difficult to dismiss as pure chance. This numismatic clue acts as a timestamp, embedding a historical marker in the very geometry of the image. Forensic overlays compare the digital reconstructions with known lepton specimens, highlighting a level of detail unlikely to be fabricated by a medieval forger. The fact that these patterns are only visible through advanced computational analysis raises questions about intentionality and capability in the era the Shroud supposedly originated. The spatial paradox deepens. The image's intensity corresponds to distance from the cloth, the background is silent, and the faint coin impressions may encode a date within the fabric itself. These findings place the formation event in a framework that is both geometric and historical, setting the stage for a forensic examination of the biological sequence that followed. Forensic biologists approach the Shroud as they would a crime scene, focusing on the blood stains scattered across the linen. High-powered microscopy revealed that these stains sit atop the image, not beneath it. This sequence is critical. Blood settled first, then the image formed. If the image had been painted or scorched onto the cloth, the blood would have shown signs of disturbance, cracking, feathering, or chemical alteration, but under magnification the edges remained pristine and the fibrils undisturbed. Chemical assays identified the blood as type AB, a relatively rare group found in less than 5% of the global population. Spectroscopic analysis detected high levels of bilirubin, a pigment produced when the body undergoes extreme trauma. These findings align with forensic expectations for someone subjected to severe physical abuse. The elevated bilirubin gives the blood its reddish hue, which has not darkened or decomposed, even after centuries. Tests for putrefaction, the chemical signature of decay, found no trace of ammonia or breakdown products. In typical circumstances, a corpse left for more than 40 hours releases gases and fluids that stain and degrade any contact surface. On the shroud, the blood remains sharply defined, with no evidence of seepage or decomposition. The image itself shows a clear boundary at the edge of each bloodstain. Spectral imaging and electron microscopy confirm that no image exists beneath the blood, ruling out any possibility that the stains were added after the fact. This order of events, blood first, image second, defies artistic technique and points to a process that preserved both biological and chemical integrity. The forensic evidence leaves little room for the idea of a medieval forgery, and instead demands an explanation for how blood, trauma markers, and a surface-level image could coexist in such precise sequence and condition. In 1988, 3 laboratories, Oxford, Zurich, and Arizona, subjected a tiny sample from the shroud's outer corner to radiocarbon dating. Their results were strikingly consistent. The cloth appeared to date from 1260 to 1390 AD. For many, this seemed to settle the question of the shroud's origin. But the story did not end with those numbers. Chemist Raymond Rogers, working with leftover threads from the same tested corner, noticed something odd. His chemical analyses revealed cotton fibers interwoven with the linen, along with traces of dye and modern starch. These additives did not match the pure linen found in the main body of the cloth. Rogers' thermochemical charts showed that the tested area retained vanillin, a compound that disappears as linen ages, while the rest of the shroud had lost it completely. To Rogers, this suggested the sample came from a medieval repair, not the original fabric. Newer methods added more questions. Wideband transmission spectroscopy and X-ray scattering, applied to other sections of the cloth, pointed to a much older date, matching linen textiles from Masada in the 1st century. Vibrational spectroscopy confirmed atomic decay patterns found in ancient fabrics, not medieval ones. The chemical mismatch between the radiocarbon sample and the main shroud undermined the certainty of the 1988 results. A second line of evidence came from Spain. The sudarium of Oviedo, a face cloth with a documented history back to the 7th century, carries the same rare AB blood type as the shroud. When forensic experts mapped the bloodstains, the geometric alignment was nearly perfect. Each stain and each trail matched in position and shape, as if both cloths had covered the same face in sequence. The sudarium's provenance and the blood alignment offered a timeline that reached centuries beyond the medieval carbon date. With conflicting datasets, radiocarbon dating, chemical analysis, spectroscopy, and cross-cloth validation, the question of the shroud's true age remains open. Each new test deepens the debate, suggesting that the fabric's story is far from settled. In a laboratory on the outskirts of Rome, a team of physicists led by Paolo di Lazzaro set out to answer a question that had stumped scientists for decades. Could any known technology produce an image on linen with the same superficiality and precision as the Shroud of Turin? The ENEA researchers turned to excimer lasers, capable of delivering bursts of ultraviolet light at wavelengths below 200 nanometers. Their goal was to mimic the chemical changes found only on the outermost 200 nanometers of the Shroud of Turin fibers, a challenge that required both power and control at the edge of what modern engineering could provide. The setup involved firing vacuum ultraviolet pulses, each lasting less than 40 nanoseconds, onto samples of ancient-style linen. At lower energies, the cloth showed no visible change. But as the team increased the fluence, a faint yellow discoloration appeared, confined strictly to the top surface. This matched the Shroud of Turin image in depth and in lack of penetration, but the process revealed a razor-thin margin for error. At just above the threshold, the linen vaporized, leaving nothing but scorched holes. The calculations were staggering. To color the surface without destroying the cloth required a pulse power on the order of 34 trillion watts, a figure far beyond any natural or historical phenomenon known to science. Di Lazzaro's team documented every trial, logging pulse widths, energy densities, and the precise onset of surface alteration. Their results showed that even with state-of-the-art lasers, only a narrow band of parameters could replicate the Shroud of Turin's superficial image. Any deviation, too little energy and no effect. Too much energy and instant destruction. The experiment did not solve the mystery, but it set a hard boundary. The formation of the Shroud of Turin image required a burst of energy delivered with a level of precision and intensity that modern laboratories can barely approach. The formation of the Shroud's image remains a puzzle at the frontier of physics. Theorists propose that only an event releasing energy with extraordinary precision could account for the evidence. One group, drawing on Einstein's mass-energy equivalence, describes a scenario where a body undergoes a rapid transformation, mass converting directly to energy in a flash measured in nanoseconds. This would generate an orthographic radiation pattern, emitting energy perpendicular to the cloth, rather than radiating out in all directions as ordinary light or heat would. The result is a perfectly collimated burst, acting only where the body touched the linen, leaving the background untouched and the image razor-sharp at microscopic scale. Others suggest a plasma phenomenon, such as a corona discharge, where millions of volts create a sheet of low-temperature plasma. This process is known to produce Lichtenberg figures, branching patterns similar to those found in high-voltage accidents. In laboratory settings, corona discharges can alter cellulose at the surface level, mimicking some of the Shroud's superficial chemical changes. Yet even these methods fail to reproduce the uniformity and the depth control observed in the Shroud fibers. The challenge deepens with AI analysis. Neural networks searching for temporal markers in the data have flagged a sub-second signal, a flash signature so brief and intense that, if real, it would require energy levels on par with modern ultraviolet lasers. No known medieval technique, or even natural phenomenon, matches the power and precision needed. The image's orthographic emission appears to defy the inverse square law, which governs how light and heat spread in space. Instead, the energy behaves as if guided by an invisible template, affecting only the outermost 200 nanometers of the linen. Physicists and AI specialists alike admit the data do not fit any established category. Every hypothesis, from mass to energy conversion to plasma discharge, faces the same barrier: how to explain a process that encodes a three-dimensional, mathematically precise image onto ancient linen, with a flash that left no trace of heat or decomposition. The mystery stands, inviting new theories and demanding evidence that matches the Shroud's silent, enduring signal. Today, artificial intelligence exposes mysteries in the Shroud that science still cannot decode. As algorithms peel back layers invisible to human eyes, the gulf between verifiable data and true explanation widens. In a world shaped by technology, the Shroud stands as a reminder. Not every answer can be engineered, and some questions grow deeper the closer we look. What do you think we are missing? Share your thoughts below.